My name is Kenny Gorman. Today, we are going to talk a little bit about Kafka. Uh, Great that there's, as Peter mentioned this morning, it's cool that we have more open source technologies being presented here at Percona World, not just MySQL. It's been growing over the last few years, and it's cool to have a talk about Kafka, I think, and hopefully you'll agree. So a little bit about me real quick. I see some friendly faces in the room that I've met before, but many of you I do not know. Like you, I am a database nerd. I mean that affectionately. I've been doing database stuff for a really long time. In '02, I had hair. Actually, when I worked together, then he can attest that I did have hair. And I was putting the pictures there, and I noticed that now I have no hair, but I'm also more cynical. And I suspect many of you are more cynical after using data technologies for many years. Anyway, my background is in Sybase, Oracle. Ran a very, very large Postgres cluster. I love MySQL and MongoDB. Was an early adopter of MongoDB at Shutterfly very, very early on. It was very painful, but we learned a ton and went on to start a company based on MongoDB. And now I'm myself and my co-founder Eric started a new company called Aventador, which is based on Kafka. So the whole notion of this talk is to talk a little bit about Apache Kafka and how it compares to the databases that you know and love. So the whole point of every one of these slides is to basically talk about Kafka, what it does, why I'd want to use it, and compare it a little bit to the technologies that you're already familiar with. And this is not meant to be an apples to apples comparison. As you'll see, Apache Kafka is very different than a typical general purpose database. And I'm going to illustrate all those components to you in the talk. But it is sort of an apples to oranges kind of comparison. In other words, they're all fruit. They're all very similar. And the patterns that I hope to show you and the architectures I hope to show you should be familiar to you. So hopefully in your thinking and your thinking about Apache Kafka, this can help guide you into understanding how you would design around it, maybe where you'd use it, maybe where you wouldn't use it or not, and help you in your decision-making process. So just real quick, how many folks are like developers doing active development? Raise your hand. Okay, and like DevOps, operations, DBAs. Okay, even split. Man, that makes it tough. Cool. All right, and how many people have heard of Apache Kafka before this talk? Okay. And how many people are using it? Like have an install and okay, so you're already familiar. Okay, cool. So we'll go through a little bit and talk a little bit about it. So I doctored this up. This is out of Wikipedia. I just kind of put my take on it. Apache Kafka is an open source pub/sub message platform developed by Apache Software Foundation, written in Scala and Java. This project aims to blah blah pub/sub message queue, architected as a distributed transaction log, blog to process streaming data. So the things I want you to pull out of here is Kafka is a distributed pub/sub message queue. It is designed to process streaming data, and its design is heavily influenced by transaction logs. And so that should be familiar to every person who's used a database. We all know what transaction logs are and how those are used. And I'm going to compare and contrast those going forward. So like I said, Apache Kafka is for high-performance streaming data. Its main use case is around distributed data movement and high-performance data movement. So what that means is if you have some sort of use case where data needs to go from point A to point B, or from point A to many other distributed components within your organization, and it needs to happen quickly, Kafka isn't a reasonable choice for that. And I'm going to talk a little bit about its architecture and why it's a good choice for that. It is persistent, so it's not an ephemeral component. It has a persistence component. It is distributed and scalable by its very design and nature. It is highly fault tolerant, and we'll talk about all the structures for these things. And it's pretty darn simple. In fact, if you come from a database background, you might actually be a little bit disappointed. There's going to be some things that are just plain missing. And those things that are missing that you're used to having are all about trying to make it very, very fast and very, very scalable. Okay, so it's a trade-off. So there's many modern use cases. We founded our company based on Apache Kafka, and the customers that we've seen come in so far, people ask, what's a typical use case? It can vary. It varies from folks doing data science workflows. Maybe they're doing sentiment analysis or doing some sort of processing in terms of a business process in data science. It ranges from just doing pub-sub coordination between microservices. It can also be used as a ETL processing pipeline, a real-time ETL processing pipeline. So, we've seen folks use inspect packets on networks. We've seen folks take LabVIEW and send data from LabVIEW in and have data science flows processed on that. So a variety of different use cases. All right. So this is the kind of the high level thing. Those of you who have familiarity with Kafka, this might be a little bit of a refresher, but let's just go through it. The real point is that Apache Kafka is designed to operate on a stream of data and a boundless stream of data. So it's not meant to be a batch type architecture like maybe Apache Hadoop. It is meant to always have data be streaming through it, and that data is being operated on, that data is being subscribed to and pulled from the system, and it's keeping track of basically where you're at in that process. It's designed as a cluster. So a Kafka cluster is built up of many brokers. Brokers live on a single machine. You can have many brokers in your cluster. We're gonna break down all the structures around this, so you don't have to sort of remember it yet. You produce data. That's a terminology. You produce data to the cluster, and you consume data from the cluster. And we're going to talk about how you send data into it and how you pull data from it. As well as there's also add-ons for stream processing. So stream processing is mutating and perhaps performing action on that data as the data is flowing through the system. And there's also various connectors that can be grafted onto the system. So I mentioned real-time ETL a minute ago. Maybe the endpoint of your pub sub queue is just to throw stuff in the database for the marketing team. But maybe also you're stream processing stuff into a front-end application that shows up on a, maybe it's some health information or like Strava or one of these health components that show up on an iPhone. So you can have multiple endpoints, multiple components built on your cluster, and its general architecture looks just like this. So the data is always streaming in, and it's always append only. So this is I'm going to harp on this over and over and over again, because if you come from a database background, this isn't going to make a ton of sense right away. You'd say, well, why would it even do that? What is this for? That doesn't seem like it's very useful. And we'll get into that more. So on the right-hand side here, I just have a diagram that shows, basically we're taking temperature data and we're adding messages, temperature. That's getting appended to a log, and perhaps something's reading that temperature and maybe has an alert or something downstream. Okay, so that's real basic high level. All right, so let's talk a little bit. Let's compare and contrast various technologies and what the various components break down as, so you can kind of get a feeling for some of the terms I'm going to use here in a little bit. So on Postgres and MongoDB, I'm going to just call it Mongo, we have the notion of a database. And a database is perhaps a collection of table spaces, sometimes not, and those table spaces are perhaps a collection of data files. We're all familiar with that. Kafka really doesn't have the notion of a database. It just has files that belong to a topic. And topic is a core construct of Kafka. We're gonna break that down quite a bit here. Postgres has a fixed schema. So you design a schema. Those tables have data types. You create that schema ahead of time, and data is put into and validated against that schema. MongoDB has no fixed schema, but does have fixed data types. So the BSON spec says, I can only have a type of X, Y, and Z. That's what's allowed in the database. Kafka is really a key value design from its very core. So you have a key that can be used to partition on. We'll talk a little bit about that. And the message itself. And the message itself can be anything. It can be an Avro message. It can be just plain JSON. It can be a binary. It can be whatever. Does not care. In Postgres and Mongo, we have tables and collections, and those are basically almost exactly synonyms. In Kafka, the core construct or namespace is called a topic. In Postgres, we have the row, which is the actual data. You guys know this. Mongo, we have a document. Kafka, we have a message. Okay, so those are synonyms there. Postgres, we have columns. In Mongo, we have name value pairs, right? So it's a dictionary or a JSON in BSON spec. It's essentially a dictionary structure. Kafka has essentially no equivalent of that. And then in terms of like just core architectural components, MongoDB has a shard, and Kafka's equivalent to that is the partition. And we're going to talk about topics and partitions. So what you really see here is we've got messages, we've got topics, and we've got partitions. And those are the core constructs that we're going to take away. All right, let's talk a little bit about how data is stored and organized on disk and persisted. So all of these technologies store files on disk. They are persistent technologies. They use the Linux or Unix file system cache. They use the underlying file system if it's on Amazon, which most everybody's on Amazon these days, I suppose, or in the cloud in some context. You're using some maybe EBS volume or something like that. But in the end, it's disk. Postgres has write ahead log. How many people are Postgres folks in here? Okay, just a little bit. So I'll be generic about Postgres and try and tie it back into regular database MySQL stuff. So similar to a bin log. MongoDB has what's called an op log, similar kind of structure. So what those structures are for is the database crashes. When it comes back up, I've got the transactions that were in doubt that have not been yet applied, can be reapplied to the database, and the database can be brought to a consistent state. Right? Fair? Kafka is a commit log. So that's the key takeaway. It is essentially like a bin log or a wall log or the op log, but that's basically it. It's an append-only structure. In Postgres, you have the file system plus buffer cache. So you may define an area of memory that's used to pull buffers from disk into memory. That memory is accessed maybe on an LRU basis or whatever algorithm that database is using. Those buffers are then returned to the client. MongoDB with the memory map file system or database engine uses the file system for a cache, so it doesn't have its own notion of a cache. It just uses the Linux page cache. And same with Kafka. So Apache Kafka does not have its own notion of a buffer cache. It simply uses the Linux page cache. And so the general use cases are as you'd expect after hearing that. Postgres and MySQL to a large degree are all mostly for random access index type workloads. You put data in, that data is fetched via some plan, returned to the calling client at some later date. Same with MongoDB. MongoDB, if you didn't know, and something like MySQL or Postgres, from a core architectural standpoint, are pretty similar. They're a generic sort of database storage engine where MongoDB focuses on the basic document as its core construct versus a row in a table. But Kafka is really designed for sequential access. So that's the major takeaway there is there's no random access path. We're going to talk about the optimizers here in a second and things like that. It's really only for putting data in and pulling data out. And we'll talk a little bit about how it knows what to pull out. All right, so topics. I said that topics, partitions are core constructs to Apache Kafka. Let's talk about that a little bit. So the anatomy of a topic is essentially it's broken down to multiple partitions. And when you create a topic, you can decide how many partitions you'd like. Maybe you'd like 1, or maybe you'd like something like 32 or 96 or whatever. It's up to you. Writes are distributed among those partitions. The person who is publishing the data to the cluster actually decides where those go. We'll talk a little bit more about that when I get into the code samples of how that looks. So partitions are simply just groups of these logs that are stored. They're distributed amongst your cluster, and the consumer knows how to pull those out. One nuance to this is that you can have groups of consumers. You can by name. So you can have marketing, and you can have iOS, and you can have whatever else. And those groups have their own offset pool. And offsets are simply the high water mark that you've pulled data from. So if I'm in a group Kenny, and there's group Bob, if I've consumed offset 1000 and he's consumed offset 100, we can continue to consume data. There's no overlap there. I'm not deleting data that he hasn't seen yet, any of that stuff. They can just consume as much as they want from that offset forward. So he goes 100, 101, 2, 3, 4. I go 1000, 1, 2, 3, 4, just like that. Make sense? So it shows a little bit of the diagram here shows a little bit of the notion of appending on the end. As we all know, that's very, very efficient for disks. That's very, very efficient for log structures. It's very easy to pop something on the end of a file and pop it off at the end of a file. There's no random access required. If we were in a spinning disk world, there's not much movement to disks for that. These days, it's mostly SSD, so it doesn't matter that much, but it's still a very optimized path. All right, so where does the performance come from? Well, I think we've talked a little bit. It's append only. That's going to give it a huge boost right there. So essentially, Kafka topics are glorified distributed write-ahead logs. The real design aspect there is that it's distributed. Number one, it's a write-ahead log we talked about, and the system itself doesn't actually have to keep track of much metadata. That's one of the sort of the beautiful things about Apache Kafka is the consumers and the producers keep track of a lot of the information. So when I produce data to Kafka, I decide what the key is, the partition key. That partition key decides what partition it lives on. The consumers then attach, they get the partition map. They can then pull from whatever partitions, and it's very lightweight. It also takes advantage of the send file system call optimization in Linux that allows the file to go right from the file system to the socket in a very efficient manner. So it's damn fast. And like I said, client-controlled routing. Any questions on that? A couple of people looking at me like, okay. So let's talk about, so that was performance. Let's talk a little bit about availability, fault tolerance constructs. So like I said, topics are replicated among any number of servers. Those servers are called brokers. Every topic can be individually configured. So this is kind of cool. Basically, a topic is a namespace. I can have a namespace for maybe my production data that's coming from, let's say I run an assembly plant and I've got an assembly line and I've got sensors on that assembly line. And I want to know if some amount of manufacturing yield is being broken or if some component is not testing correctly. And I want to know right away so I can shut down the line or I can update forecasts or I can update a dashboard. Maybe what I do there is I have a topic for that particular line. So there's a line for phones and one for tablets. Maybe that's what I'm making. And I want to differentiate between the two. I might have a tablet topic and a phone topic. Okay. And they can each have their own level of both replication. So you specify, let's say, replica level 3. So it'd be 3 replicas of every partition. And you can also say how many overall partitions. And there's sort of a strategy here. It's sort of like, let's say you have 100 brokers. You may have 1,000 partitions with a replication factor of 3. Okay, so that would interleave partitions amongst all those brokers and all those servers and give you, essentially very, very good fault tolerance. All right, so how do these clusters decide who's failing and how to fail over? I'm going to compare it with Mongo here because that's kind of the closest cousin. So in a failure scenario, in Kafka, you have a leader. That leader is essentially the master or the primary, the one doing all the work, shuffling the data out to the consumers. If one of the brokers fails, a lot of partitions will be affected, right? Because there's multiple partitions on that. All those partitions will go dead. New leaders will be pulled up on other brokers, and those leaders will continue the workload from there. The way that's done is there is a set of replicas that are in sync, and those replicas essentially do a consensus. And that is stored in Zookeeper. You're probably familiar with Zookeeper if you know Zookeeper. Zookeeper is a critical component to Kafka. It's required essentially to handle the failover in this case. MongoDB has a majority consensus. That's their protocol or their design. In 3.2, there's some other Mongo folks that know, Kimberly's here, that know Mongo 3.2 very well. It's more Raft-like in its protocol. But either way, it's a very modern consensus protocol that allows for voting, allows for masters to be elected. All of these protocols have switches to tune them. How long do you wait until you make a decision? How long do you take failover? If you do a failover, how quickly do you fail back? Things like that. I think that's that. All right. So let's talk about the traditional insert, update, delete kind of stuff here. So in Postgres, and I won't belabor you with all this. You guys know this stuff. But in the insert, you insert into a table, you execute. So that's basically a string that you send a SQL statement into. This is in this case, it's pseudocode for psychopg2, which is Python and Postgres. So in this case, it's just a string. I'm inserting into a table. I'm executing that SQL, and then I'm committing that insert. Right. So there's an ACID component to that. I can insert multiple things and roll back. I can use all the constructs of doing transactions that exist in modern relational databases. MongoDB does not have that. It is essentially atomic for that one operation. So I say save, and I send it to the database. That either succeeds or fails on its own. There's no commit component. And Kafka's kind of more similar to Mongo in that regard. There's no transactions. There's no sort of commit or rollback components or design. It's simply just like send this data to Kafka, and I'm done. You can do it asynchronously. There's switches for doing it in an asynchronous fashion. There are switches for doing it to multiple partitions. So if you have like 3 replicas, you can say, give it return when I get all 3 replicas. Something like that. So there's various switches to that and various modifications to that, but the core construct is just send and then the topic that you want to send it to. Okay. Query, again, similar kind of thing. I'm doing a select, and then in this case, I'm pulling back a cursor and I'm iterating over the cursor and printing that particular component of that cursor. MongoDB, same thing. And Kafka, a little bit different. You're actually pulling something back from a topic. And then you're saying, I want to subscribe to a topic. I want to pull back all the messages from that topic. And what's interesting here is you may not start getting data right away. This is a nuance that surprised me when I started using Kafka. You might say, go ahead and start consuming data, and there's nothing there. And just sits there and waits for something to happen. And then, the messages come. So very, very different paradigm from using a relational database in that sense. If that happens to you in a relational database, you're like, oh, I forgot an index or whatever else, right? So you're going to go check it, because if it's taking that long to return, something's wrong. Anyway, a little bit different nuance there. Update, same kind of thing. Similar thing in MongoDB. There's no updating in Kafka. There's no ability to mutate data. It's append only. Same thing with delete. Okay? So this is the kind of typical construct if you were coding against a database that you might do. In this case, it's Python and psychopg2, which I think is fairly common. It looks similar. This kind of construct should look similar across MySQL and Oracle and everything else. In this case, I'm connecting to the database. I'm building a cursor. In this case, a dictionary cursor. That's an array of dictionaries. I'm taking a string. That's a SQL statement. That statement then gets executed. So it goes into the database engine. That thing gets parsed, gets turned into a plan. That plan gets executed. Maybe I'm using an index on that plan. Goes and fetches buffers. Buffers come back from disk. Go and get the actual row from the index fetch. Bring back the row. Give it to the customer, or give it to the calling client. In this case, I'm fetching all those cursors, and then I'm just looping over them. Okay, so that's kind of the parse, execute, fetch life cycle of a traditional database. It's a little different in Kafka. So this is the publish side. So that was the query side of the relational database. This is the publish side of Kafka. In this case, what I'm doing is I'm creating a producer, and this is actually Kafka Python. So it's a driver for Kafka. It's Python. So what I do is I specify the bootstrap servers. In this case, it's a little different. You just have to have one member of the cluster. They all know who's the leader. They all know where to fetch the data, and they all advertise that. So you hit one of those brokers, is going to come back and tell you what you need to do or how to proceed. And in this case, once I've subscribed to that, or once I've defined that, I can go ahead and just start sending data into it. And in this case, it's almost like UDP. I'm just sending the data. I'm not asking for ACK. I'm not flushing. I'm not asking for multiple members. I'm just sending data. So the cool thing is it's configurable in Kafka. You can run it in a UDP-like kind of way, or you can run it in a highly reliable way by saying, hey, I want to flush data, and I want to wait until you get to all 3 members, and then you can come back to me. Another take on this is, in this case, I'm not setting any keys here in the send. I'm just saying, hey, round robin across all the partitions. I'm not actually creating a key to hash on. You can also specify, like, let's say there's a username or a some sort of type, like maybe in the example of the lines of manufacturing lines, maybe one of those keys is like, the part number or the station. You might hash on that and then get a nice distribution across all partitions. Okay, so I think that is that. So and subscribing or consuming is very similar. Again, same kind of construct. Again, in Python, I'm going to connect to the cluster with the bootstrap servers command here. I'm going to subscribe to a particular topic, and then as those messages come in, I'm going to consume them and just print them in this case. So let me show you another example here. So this is a little bit more complicated, but this should help illustrate what I was talking about a minute ago. So in this case, while it's running, I'm going to go ahead and poll and continue to process. So I've got a little timeout in there just so it's not super aggressive, but we can make it as aggressive as we want. And all we're basically doing is pulling back continuously that information, and the program's always running. So if you're running some sort of a learning component, or maybe you're powering dashboards or something like that, you don't actually want a real kind of polling. You don't want to sleep. You don't want the process to sleep, the calling process to sleep, wake up, and then go search for messages. It's just always consuming messages. This is the kind of construct that you may have. All right, so let's talk a little bit more about offsets. In this case, I'm not actually calling out a consumer group. Using this example, I could actually specify a group name here, okay? And that would allow me, again, to have a different offset pool than my neighbor or some other process. I think that's pretty good for that. All right, so let's talk about tooling. So that's the basic design stuff. That's how it works. We've talked about topics. We've talked about partitions, fault tolerance, and performance. Let's talk about how we kind of operate a cluster and how we interact with it. So there's no simple shell to Apache Kafka. There's no simple way to connect and just issue commands and ask for things and inspect data. There's no schema, so it's hard to like describe tables or things like that. There's no shell like MongoDB has, where it's got a JavaScript interpreter to kind of show things as well and run various commands. It's a Java program that has sort of none of those constructs. So it's I made this up this morning, I'm going to forget it. Big old fucking Java class in shell scripts. Something. Anyway, on Kafka, there's a directory that has a bunch of shell scripts. And those shell scripts are basically like helpers to various Java classes. And so you're basically calling Java, you're calling a class with some switches, and those switches basically, do whatever you want. Maybe you want to publish a message. Maybe you want to subscribe. Maybe you want to change the topic design or create a topic. There's shell scripts for all those things, and that's kind of the common design pattern. So when you install Kafka and you want to go mess with it, you go into the directory /bin. There's a bunch of shell scripts in there. Just poke through them and look at them. They're all very well documented into their operation. But as a DBA or as a database person, it's going to be different for you. You're going to look at that and say, oh, okay, there's a bunch of scripts to run that do things instead of having like this general purpose shell. Make sense? We use a bunch of tools in our shop to operate Kafka and mess with it. One of the hardest things that we found is just show me like a couple messages. Like show me what's in there. I don't even know what's in a topic. Like, what does it look like? And so Kafka Cat's a utility that's killer. It's based on the librd Kafka, which is the C driver. It's a command line utility, runs on Unix, on your Mac or whatever. It's easy to use. You can call it with switches like I want to publish a message, and you can like cat some JSON through it. Or you can subscribe to a topic and consume messages, and it's got switches for whether you're what consumer group you want to be in or whatever. So it's very, very flexible, great tool. Like when you download Kafka Cat at the same time. Like they should be together. They're great brethren. We also use JQ a lot. I don't know if you're familiar with JQ. Has anybody used JQ? JSON? Yeah. Okay. So that's a killer utility for spooling JSON to the command line. Yeah, one of the biggest use cases for Kafka is just to put JSON into Kafka and send it somewhere, and then have someone do something with it. That's like, I want to say, like the 80% use case. And so Kafka Cat and JQ make it like, I just want to pop a message off. I want to look at it, format it, see what's going on here. Those two tools are fantastic. Like I said, there's a bunch of shell scripts. There's also utilities like Mirror Maker, which allows you to mirror clusters. Say if I have two Amazon availability zones and I want to mirror between them, you can mirror Kafka using these types of tools. And also in our shop, we use PrestoDB quite a bit. In fact, our product has it built in. Everybody familiar with PrestoDB? Hands? Everybody heard? Okay. So PrestoDB is a Facebook project. It's a distributed SQL query front end. I might be murdering this a little bit. This might not be the official line, but that's what it is. It operates kind of like a batch job. You issue some SQL, it sends it off. It runs it across the entire cluster, returns the results, and it's got a nice connector for Kafka. So if you're a DBA and you like using SQL and you want to describe a topic, you can do that in PrestoDB. In fact, you can just say describe the topic as if you describe a table, and it will look just like MySQL. The commands are the same as MySQL. So it works great. Facebook folks built it. All right, that's that. All right, so let's talk a little bit about sort of settings, tunables, kind of DBA backend stuff. Something like Postgres or MySQL, again, has sort of this time-tested model. There is some memory region where you'll have shared buffers that most engines, not all engines have this, but this is very common. We'll have some memory space. In Postgres, it's shared buffers. Oracle has buffer pools where the pages from the data files will be pulled into memory. They're kept as a cache and they're operated against for the database engine itself. There's also structures for recovery, write-ahead log and recovery. I talked about that. If the instance crashes, when it comes back up, that's replayed. This is very, very common, and those are the things you have to set for, say, Postgres. You want to set that memory region. You want to set your recoverability component. In Postgres, you want to decide if I'm running a slave or not. If I'm doing replication, there's different switches for whether or not I'm running a slave or a replica. And then you need to size that memory region. By default, it's way too small, and most everybody hacks on it right away. MongoDB in the memory map v2 engine. You don't need to size that memory region. Like I said, it's using the page cache as its database cache, which also means it's not double buffering. It's interesting. In that one, we typically set database per DB in order to get DBs to be in the file system in a nice, clean way. That's kind of like your choice, not a big deal. And there's some file system tuning that we've had to do in the past for various Mongo clusters, whether it be write ahead or read ahead or write back, cache tuning, or whatever. Can't remember now. Anyway, Kafka has only a few things you really need to set sort of out of the box. You can operate it on your laptop or as a developer right out of the box and not have to worry about it too much. The thing that maybe I didn't explain too well, but that's very important to understand, is that I said there's no deletes, right? So like, how does data get purged out of your cluster? Does it just grow forever? And the answer is no. There's a cleanup process that goes in and wipes that data based on a timestamp. In fact, you're in control of it. In this case, you might set log.retention.hours and say, I want it to be 4 hours. I think by default, it's 7 days. So if you start putting data into Kafka and it's on your laptop and you come back 7 days later to play with your project and the data's gone, it didn't fail. It did its job and it nuked that data. So that's a setting that needs to be configured. Obviously, you need to think about your disk space and capacity plan for that, because it's just appending to logs, and once they get that old, it's just going to start cutting off the backside of them. Obviously, that's very efficient too, right? Okay, and then a little bit of Java tuning. I think we set our XMS value, which is the max memory region for Java for the JVM, to about 90% of available memory. give or take. It depends on the workload, depends what you're doing, but that you might start there and just try that. So those are some settings there. All right. Let's see how we're doing on time. 6. All right. I think that is kind of that's kind of it. Love to answer some questions if you guys had questions. I would encourage you to hit the documentation. There's way more to. I tried to go very simply through the whole stack. There's way more to Apache Kafka than I alluded to here in terms of settings and tunables and offset management, asynchronous behavior. Those are the kind of things. If you want to do those kind of things, read more about those, or I can take your questions about them, or you can come see me. Also, we're hiring. If you like Kafka enough to do it for a living, we'd love to have you come help us do it for a living. So. Questions? Yeah, so there's a couple things to think about. I'll address I'll address that in two parts, I suppose. The question was, what about durability of Kafka, or lossiness, as you put it, in Kafka? And what about when I'm mirroring between availability zones? So first part is that, like I said, Kafka cluster is not totally in control of how you put data into it. As a consumer, or a publisher or a subscriber, you're in control of how you want that to look. So when you create a topic, you can create replicas and you can decide how much to replicate the data. You can also say, I'd like to wait until this is on those replicas before I actually publish the data. You can also say, I'd like to actually wait for the whole thing to come back and acknowledge that I've written that data. So you're in control on the publish side as to how, what level of replication you want. So that's go ahead. That's part one. Sure. Yes. Great question. Great question. So the other part of that is, are you in control on the consume side? And the answer is yes. The way that works is you're managing your own offsets. So the offset is essentially the high water mark of how far you've read through those logs. If you get some data, you have an error, you're in charge of whether or not you commit that new offset. So you can run it in sort of auto mode, like we've all used auto commit. Yeah. Okay. Yeah, you're nodding. It's similar to auto commit if you don't actually manage your offsets. You don't have to. But if you really want that ability to sort of try, accept, and then retry, then what you would do is manage your own offsets in the code, and you could retry that offset if there was an error or some condition that didn't work. So that's kind of the core construct of that. Number two is, how do I do that between regions with MirrorMaker? MirrorMaker is not my expertise, I'll be honest with you. I'm not entirely sure, but I will hook you up with someone right after this if you want to see me, and we can talk about it in detail. Right. So the use cases vary. That's the weird thing about Kafka. Going into this, we thought, whatever, year and a half now, just a personal anecdote, I kind of fell in love with Kafka for the same reasons we've gone through here. It looks a lot like the things I'm used to. This is neat, and it's also really effing fast. So cool, let's use this for stuff. And that was kind of the initial thing that got me excited. The customers kind of have that same aha moment where maybe it's only certain workloads. Like, I want to be real careful. This is not a replacement for databases. This is not a replacement for MongoDB, right? This is another technology that you all can use in conjunction with perhaps with these systems as you build your company's infrastructure. So I don't know if that's really answering your question or not, but that's kind of where I come from. Oh, I see. It can be used for anything. I mean, it sort of just depends. Real-time ETL processing. So if people are taking data out of a particular data store or from a front end, increasingly like maybe even a web app or a desktop app will generate data that needs to be ETL'd into some other reporting source. So Apache Kafka works great for that. You just put the payload in the message and send that along. You can mutate it through stream processing. You can route it through Kafka to various consumer groups, to various endpoints. So that's a nice kind of use case. Another one would be, like I said, manufacturing. More and more these days in manufacturing, real-time data matters. You can't wait for to see your yield or see what's broken tomorrow you start a business, and because you processed it last night, you need to actually know what happened right now, and we need to shut down that line or change it or change the machinery or whatever it is. And that's what because the profit margins of manufacturing have changed. So this driving, the real-time data has more value in that sense, and it's driving those kind of use cases. So real-time manufacturing is another one of them. I'll say IoT. I'm sorry I said IoT. I didn't want to do that here. It's being recorded. But like sensor data is another natural attribute. I want to send maybe temperature sensors or accelerometer data, and I want to be able to route that to various components that are processing that and deciding what to do on it. Maybe it's a data science workflow. Maybe they're doing some sort of deep analysis on that, and then adjusting some application based on that. So that's another one. And we've even seen stuff in oil and gas. Now we're in Austin, Texas, so you'd think oil and gas would be obvious one, and we've started to see folks use Kafka for that kind of use case as well. It's interesting. We didn't know, sort of anecdotal here, we didn't know that oil rigs and drill bits generate, I'm sort of super naive to it, I didn't know that they generate thousands and thousands of data points. I think most people know that like jet engines do, but like we didn't know drill bits do too. And so that's another use case that customers have adopted, that they're sending data, and they're very expensive. So if something's going wrong, or there's some temperature anomaly, or there's some vibration anomaly, they want to know right away so they can adjust the RPM, or so they can shut it off, or they can call maintenance, or whatever it is. And they're even doing it for analysis, for like real-time analysis for timing out of components. So they said like, this thing's ding, this thing's reached 2,000 hours, we know it's dead, pull it out, put the new thing in, things like that. So a lot of different use cases. That, yes. It depends. I mean, we see front ends being all over the place, and they'll typically use a native driver or like a REST endpoint, and they'll just like UDP style toss random events into Kafka. It's a nice place if you're an application developer to say like, I don't care about this. I'm just going to throw it out there, and the business can pick it up later. But at least I'm emitting the events I need to emit from my particular component. So from a services standpoint, that's a nice demarcation, I guess. And then we see on the consume side various processing components pick it up. Maybe it's a business logic that combines it with some other stream and then deposits it in a database or something. So that's a real common. Right. So the question was, what's the real world latency? I don't know, man. I mean, that's one of those things that's just so use case dependent. And if I say a number, someone's going to say, "Oh, Kenny said da 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 da." So, the thing that really makes a difference here is not necessarily like the thing I would think about there is that when you have a component that's continuously processing data, the overall latency, whether it's on the wire or whether it's that processor or whatever it is, or Kafka itself, is going to be greatly advantaged over something that's sort of like insert and query in its very core. How much that matters? It depends on your infrastructure. It depends on the network topology. It depends on everything. But the advantages that Kafka has is, A, it's append only, so you're not doing random access type situation. It's continuously processing, so in a lot of cases, the latency of just waking up and deciding to do something is a benefit too. So, that's the best answer I can give you, to be honest. Right. Yes, it's a good question. Yeah, right. So the security slide would be a little gnarly because it's there's been a lot of security breaches with high profile ones recently with MongoDB. Kafka has a fairly robust security component. It is the SASL based stuff is with the latest release is now a possibility. Like a lot of these technologies, it didn't start off with like a super robust model, and they've kind of got to that point. But now with 10.02, I think we're starting to see where we feel better about it. In our service, we actually have an ACL in front of everything. So when you create a Kafka cluster on our service, you actually have no access to it. You actually have to go open up an ACL. You have to say, CIDR mask, whatever, your network is, and then you can consume data or publish data to it. So we added an additional layer, but it has stuff built into it, and SSL. That is just starting to be pulled into the fold. So the later releases are starting to do that with SASL and fine-grained access control. Exactly. Yeah, good question. Yes. Yes. This is the question. This is a great question. So the question is, how if your partitions are the unit of essentially parallelism and scalability. So how do you then know what to set it to, or how do you design for that? Good question. And the answer is you need to test. We find customers. So remember, Kafka can run on boxes, based on what we just talked about, a lot less expensive than the regular database box. So provisioning a few more boxes and building a little bit bigger cluster and having more partitions has a very low downside relative to maybe a traditional database. So, over provisioning in that sense and just saying, like, let's make this 32 partitions because I've only got 2 consumer groups and they're only 2 daemons each or 2 services each. So why do I need 32? I could just get away with whatever, 4. You just make more. There's going to be no downside to that really until there's some theoretical limit. I mean, maybe if you went 2048 or 10,000 or something, you'd start to see that. But we haven't really seen that in practice, frankly. So very common to build a cluster with like 4, 6, 8 brokers and then partitions with like 32, 64, 128 or something like that. Very common pattern. And a few topics. Maybe not 100 topics, but like 8, 6, 4, something like that. From that side, it doesn't matter as much. The consume side is the one to really think about. The number of consumer groups and the number of partitions that you have per consumer. That's the equation that matters the most. Good question. Back. Right. Good question. Is there rate limiting per user, per producer? I think the only thing there, and can't quote me on this, is that there are back pressure controls. But it might be a storm feature. I don't know. See me after. I'll hook you up with someone who can help you. I don't know. Good question. Anybody else? Yeah, sure. So typical deployment model is, we like to have redundant zookeepers. We typically deploy. So in some cases, you'll deploy like 1 broker and 1 zookeeper. You can do that. That's obviously not redundant. Has no, HA characteristics. 3 zookeepers tends to be a reasonable configuration of a cluster up to whatever n, up to some realistic limit that's very high. So typically, almost all of our deployments have 3 zookeepers, and then whatever many brokers that folks want. It's worth noting that zookeeper requirements in the earlier version of Kafka were a little bit heavier than they are now. So folks who have been writing Kafka and engineering on it have been pulling components out of Zookeeper, or at least the option to use Zookeeper to a higher level so that it's much more efficient with the traffic to Zookeeper. So one of them in particular is offset management. Offset management is now within Kafka and used to be within Zookeeper. That makes sense. 1 minute left. Anything else? Okay, awesome questions. Thank you guys. Appreciate it.